While in-memory databases use main memory for data storage, disk memory databases use physical disks to store and access computer data. In-memory databases were created to increase the performances of organizations that deal with large amounts of data. The first and largest advantage of in-memory databases is speed. In-memory databases search and retrieve data much faster than slow-spinning hard drives. In-memory databases utilize dynamic random access memory, also known as DRAM, which eliminates a lot of issues that traditional databases experience, such as design issues and synchronization. This allows DRAM to sort data at a much faster rate. Another difference that in-memory databases make is they increase an organization's ability to make real-time business decisions. Since in-memory databases are so fast, businesses always have relevant and timely information that they need to make decisions when dealing with customers, suppliers, or management. Before in-memory databases, businesses had to wait for information to return or base their decisions on outdated information. Needless to say, in-memory databases provide a significant competitive advantage. The other significant advantage in-memory databases provide is that they reduce burden on a company's IT resources. Disk memory databases can be enormous given the amount of data they hold. Large and expensive server hard drives require a lot of installation, maintenance, and storage costs. In-memory databases, on the other hand, require less storage and have a lower cost of memory. Additionally, they do not require constant maintenance, which also helps save IT resources. Traditionally, there are 4 requirements of database transactions. They are atomicity, consistency, isolation, and durability. The first requirement, atomicity, means that all transactions must be all or nothing. So if one part of the transaction fails, then the entire transaction fails. A system must guarantee atomicity in every situation, including power failures, errors, or crashes. The next requirement is consistency. This means that any transaction will bring the database from one valid state to another. The database's constraints must not be violated, and the transaction must be performed accurately, correctly, and with validity. Isolation is the next requirement. This means all parts of the transaction must be the same, as if those parts had been done separately and sequentially. The last requirement is durability. This requires that once a transaction has been committed, it will remain committed through any event, such as power loss, crash, or error. Durability is the requirement that in-memory databases often have trouble meeting. Since many in-memory databases are volatile memory-based, they lose all information if the device loses power or is reset. Due to this, in-memory databases must add durability in various ways. To improve durability, a number of mechanisms have been devised. Snapshot file, also known as checkpoint images, record the state of the databases at any given time. These snapshots are done periodically and when the database does a controlled shutdown. While snapshots can improve durability to an extent, they don't preserve the most recent information that was recorded after the last snapshot. Another mechanism for improving durability is transaction logging. This records changes to the database in a journal file and makes the automatic recovery of an in-memory database easier. Non-volatile RAM is another module. This is in the form of a static RAM that is backed up by battery-powered RAM. This allows in-memory databases to recover data after rebooting. High availability also helps improve durability. High availability relies on database replication to protect against data loss. In the event of a database failure, high availability keeps an identical standby database. High availability and its replication is often used in combination with one or more other durability improving mechanisms. Oracle began its journey in 1979 as the first commercially available relational database management system, or RDBMS. Oracle's name is synonymous with enterprise database systems. It's known for unbreakable data delivery and fierce corporate competition with their CEO, Larry Ellison. The current Oracle release is Oracle 12c, and the C stands for cloud, which is reflective of Oracle's use of cloud technology. The second leading in-memory database systems is Microsoft SQL Server. SQL Server is known for its ease of use, availability, and tight Windows operating system. Microsoft also advertises this server as the platform for on-premises and cloud databases. Another industry leader in this field is IBM. The latest release of DB2 is widely compatible. It runs on Linux, Unix, Windows, and the IBM series and mainframes. IBM DB2 is also less costly for consumers. Users that switch from Oracle to IBM DB2 spend up to 80% less in their first year alone. DB2 users save around 30 to 39%. Another advantage that DB2 has is that it comes with IBMS support. This comes with frequent and thorough software updates and patches. IBM is known for their high-quality software support, and this carries into DB2. To conclude my presentation, I'd like to recap what I talked about. I discussed the difference between in-memory databases and disk memory databases, as well as imdb's advantages. I talked about the 4 properties required for database transactions: atomicity, consistency, isolation, and durability. I also discussed how IMDb's improve their durability. Lastly, I went over the industry's top leaders and what each company offers.